In this video, I'd like to introduce Riemann zeta function and the famous Riemann hypothesis, which arguably is the biggest mathematical problem yet to be solved. It is one of the 7 Millennium Prizes problem that there's a $1 million prize on it. So let's look at it and see if we can solve it. Okay, so it is called Riemann zeta function, but it was first introduced by Euler, Leonhard Euler, who used it to study prime numbers. So somehow this function is related to prime numbers. He used this function to show that if you add up 1 over all of the prime numbers, then it's a divergent series. So in particular, this shows that there's infinitely many primes. Otherwise, the sum could not blow up to infinity. And he also tells you about how much prime numbers are out there. So it says something about its distribution as well. Riemann, Bernhard Riemann, used this function, this zeta function, to get results about like a more like an accurate, precise asymptotic distribution of primes. Okay, so just so we're on the same page, if we add up 1 over n for every natural number n, then it diverges. So that's the famous harmonic series. But if you look at a power that's higher than 1 in the denominator, so if we look at a 1 over n to the s power, where s is strictly greater than 1, then it converges. So let's first show why that might be true. What we could do is we could use what's called the integral test. So let's say we have the graph of 1 over x to the s. The first term in the series is equal to 1. And then this curve passes through that corner. And then this is, so all of these rectangles has the height 1 over 2 to the s, 1 over 3 to the s, and so on. So this sum is going to be less than 1 plus the integral above these rectangles, right? Because the integral covers the rest of the rectangles, except for the first one. And it's nice to compare with the integral because we could actually compute the integral relatively easily. So we just have to use the power rule. So we add 1 to the power, divide by its power, plug in x equals to 1, and then plug in something that blows up to infinity. Note the power over x here. As long as s is greater than 1, then you have a negative power, which means if x blows up, that approaches 0. Because it has a negative power, it's blowing up in the denominator. So therefore, we just have the term when we plug in 1, we'll be subtracting. So I'm just gonna switch the denominator here. And this is a finite number as long as s is greater than 1. Okay. So now let's consider this function with complex exponent s instead of just the real number s. And we're going to call this the definition for the Riemann zeta function. And as long as the real part of s is greater than 1, this thing will converge. So let's show why that might be true. Okay, so to be clear about how do you take a number to a complex exponent, the way to do it would be just kind of define it this way. So n to the s is same thing as n to the natural log of n to the s, because en logs are inverse functions. And log function has the property that you can bring the exponent to the front. So make this the definition of complex exponents. N is a positive number. So when you plug it into the complex log function, that's the same thing as natural log. And now this is a perfectly well-defined expression. So we're gonna take this as an expression, the definition of n to the s power when s is a complex number. Okay, so when does this converge? Well, let's see when it's absolutely convergent. So we look at the modulus, and then this is the definition of 1 over n to the s. And note that when you plug it into the complex exponential function, the modulus is given by the real part of the exponent. So this is the real part of the exponent. The natural log of n and minus sign is, you could pull that outside of the real part. And then this is the same thing as 1 over n to the real part of s. And we know that this converges when real part of s is greater than 1, right? So as long as, let's see, let me draw the complex plane. The real part greater than s would be the right-hand side of this line. So some of you might be thinking, hey, wasn't power series only convergent on circles? That's still true. This thing is not in the form of power series. So this thing is convergent on the right-hand side of the real part of s equals to 1. Okay, all right. So that's the zeta function for this part of the domain. It turns out that you could define this function for a larger domain. You can extend this function in such a way that it could be defined for all of the complex number except for s exactly equal to 1. So as long as you avoid that point, you can make sense of this function and you can extend it for a larger domain. And he used the technique of analytic continuation, which we described last time. Okay. So that is a little bit messy, but you could actually extend to slightly further. So just to the right half plane, using the following technique. So what we could do is look at a partial sum of this zeta function, and then also look at the integral on the same region of 1 over x to the s, kind of like how we did with the integral test. We're kind of comparing them, but they're a little bit off, right? So so this time I'm going to put the rectangles to the right of the curve. So if you look at the integral under the curve, that's less than what we would get if we add the rectangles. So these shaded region of the rectangle that's sticking out above the curve 1 over x to the s, we're going to call that delta n of s. Now, I know I'm kind of drawing this like this is the real function, but s could be complex. So we are just going to define delta n over s as the difference of these two terms. Okay. Now let's take the limit as n goes to infinity. So on the left-hand side, we get something that converges to the zeta function. That's the definition of the zeta function. The integral will converge to 1 over s minus 1 because we were able to compute that. And we have this sum of these delta n's. It turns out that you could show that this thing is analytic and it converges for as long as the real part is positive. So it's defined for a slightly larger region than the zeta function. So we're going to call whatever it converges h of s. So we have this equality here. The zeta function is equal to 1 over s minus 1, which blows up at 1. And we have some other analytic function that's defined for positive s. Sorry, the right half plane. But if you kind of look at it, so this equality holds for s, real part of s greater than 1, but the right-hand side is defined for real part of s greater than 0, right? This is defined for any s that's not equal to 1. This thing is defined on the right half plane. So we could actually, we have two analytic functions that adds to something that agrees with the zeta function for real part of s greater than 1, but we have extended the definition of this function to the right-hand side, right-hand plane, except for the blow up at 1, which happens on this 1 over s minus 1. Okay. So here's a theorem. So the only zeros of zeta function outside of what's called this critical strip. So everything between the real parts 0 and 1. So this is the part that we just extended the function by. Anything outside of this could only be zeros on the negative even integers. Okay. So you could show that the zeta function is equal to 0 there. And then the only other zeros could be inside of this critical strip. Okay. And understanding where the zeros are on this critical strip gives you lots of information about prime numbers somehow. Okay, so here's the, so it turns out that if you can show that there's no zeros on this right edge along the line, the real part equals to 1, then that's equivalent to proving prime number theorem, which we'll talk about later in this video. Okay. So the Riemann hypothesis, so this is the $1 million question, literally. In this strip of the real part between 0 and 1, all of the zeros of the zeta function lines up at the real part of s exactly equal to 1/2. Okay. So not only that all the zeros are in there, the zeros are exactly down the center on this critical strip. So lots of research has been done. So you could show that there's actually infinitely many zeros in there, and we've found lots of them. I know there's infinitely many zeros, but 1/3 of those zeros has to be on the line. So that has been proved. But actually, so far, everything's been on the line. So trillions of zeros has been computed, and they all lie on this line. And it's not in a regular interval either. It's scattered along that line. So the Riemann hypothesis is on the list of the 7 Millennium Prize problems. One of them has been solved so far. That's the Poincaré conjecture, proved by Grigory Perelman, a Russian mathematician. And if you know where the zeros are, it has some strong implications about the distribution of prime numbers. So let's talk about what prime number theorem is. So this is something we can prove about the prime numbers that we do know. So let's say pi of x. This time, this pi is not 3.14159. It's the number of primes less than or equal to some number x. So pi of x is called prime counting function. So for example, pi of 1 is 0. And pi of 2, so 2 is the very first prime number. So pi of 2 is equal to 1. Pi of 3 is equal to 2 because it's the second prime number. And 4 does not add to the prime, so it stays at 2. And pi of 5 is 3 and so on. So this is prime number function. So it kind of, it's like steps. It'll count how many primes for x less than or equal to x. And then the prime number theorem says that the prime counting function behaves like x divided by natural log of x when x is large. So this squiggly line here, I mean asymptotically. So the precise definition of this is that if you take the ratio of these two functions and take the limit x goes to infinity, then the limit is equal to 1. So in the limit, they're nearly equal. Okay. All right. So again, Euler introduced the zeta function and the prime numbers. And Legendre and Gauss looked at the prime number theorem, or actually they counted a whole bunch of prime numbers because they were, of course, interested in it. And they conjectured that the prime number theorem is true. So they had guessed by the enormous amount of computation them and their students have done, that it's very likely that the prime number follows this distribution. Okay. And the Riemann wrote a very legendary paper on 1859 on the number of primes less than a given magnitude. He extended the zeta function to everything but 1 and introduced lots of really good ideas. And initially, people didn't understand the importance of this paper, not quickly enough. But after a while, Hadamard and Poussin used ideas in the paper to prove the prime number theorem. So I keep saying that there's a relationship between zeta function and the prime numbers. I haven't shown you exactly what that is. So let me try to show that. So zeta function looks like this: 1 over n to the s power, and we're adding all of them. We're adding all of natural number n in the denominator to the s power. But every natural number could be a product of different prime numbers. So another way to write this is look at the product of all the different powers of primes. So this is 1, 1/2, 1 over 2 to the second power, and then 1 over 2 to the third power, so 1 over 8s, and so on. So all the powers of 2 is here. All the powers of 3 is here. all the powers of 5 is here, and so on. So you multiply over all the primes, where 1 over p to the k, we look at all the powers of those primes, and then you raise it to the s power. The reason why you can factor it like this is because every natural number is uniquely a product of some combination of prime powers. So when you multiply all this out, you get all of the natural numbers, exactly one time each. Okay, but if you actually kind of write it this way, this is a geometric series, 1 over p to the s to the kth power. So if we know how to compute the geometric series, it's 1 over 1 minus the ratio, and ratio is this here, p to the negative s power. And now you can see that the zeta function actually could be written as the product where we're running through all prime numbers, 1 over 1 minus prime to the negative s power. So at least this representation of the zeta function shows you that prime numbers is related to it somehow, right? Okay, so just kind of run through of like how this prime number theorem is usually proved. We want to show that they're asymptotic, or actually, instead of this function, you could say, well, it's actually similar to this logarithmic integral function, Li, which is the integral of 1 over natural log of t dt from 2 to infinity. And then show that it's actually asymptotic to that guy. The proof is beyond the scope of this course. In fact, actually, it was a capstone project of a different student, I think 3 years back. But you could show that the prime counting function is roughly this logarithmic integral function plus some error term. And when you write down this error term, von Koch actually wrote down a really precise way to write down the error, assuming the Riemann hypothesis is true. So you could write it in terms of the zeros of these zeta functions. So like if the Riemann hypothesis is true, we actually understand the error terms very well. Yeah, and I think this is where we're gonna end the class. I hope this sparks some interest. The prime number theorem is very beautiful theorem, and complex analysis gave us the tool to prove it first. So there are other proofs known now that you could avoid complex analysis, but it's hard without complex analysis. It has amazing power, and it gives you insights about other subjects in mathematics. All right. Okay, I think this is where we're gonna end. I'll see you later.